And last, we have objective 3. We want to graph polar equations by plotting points. So we can also graph polar equations by plotting points using theta as x and r as y to graph the unique shapes of polar equations. So this isn't our typical equation form where we have y is equal to something times x, something like y is equal to mx plus b for something like this. So we're treating our theta as x and r as y, since we normally write our polar coordinates out, or polar equations out, as r is equal to some number times sine or cosine of theta. So if we're going to get these unique shapes that are corresponding to polar equations, we would definitely want to classify the different shapes that you can create using your polar equations. So the first thing you can do is you can graph lines on your polar coordinate system. So we have lines passing through a certain pole, vertical lines, horizontal lines, fairly straightforward. Then we have here our circles. So we see circles centered at the origin, circles off-centered by either x or y, so shifted horizontally or vertically. And then we get into our more difficult shapes, and these are going to be our other equations. So we have, technically in this table, we have 6 different types of equations that we can really see when we have polar coordinates. So first thing that we can see is called cardioid. This looks a little bit like a heart. You can also think of it as just a circle with a dimple in it. But basically the polar equations that the cardioid reflects is going to be r is equal to a plus or minus a times cosine of theta, or a plus or minus a times sine of theta, where a is greater than 0. So we see a is greater than 0 in both of these cases, and we can just switch out either cosine of theta or sine of theta, and then we have that plus or minus sign. Then, and I'm going to try and say this right, limaçon without inner loop, so it's French. So it looks like a cardioid. It is just centered at the origin now instead of the dimple being at the origin. So we've shifted it a little bit, but in this case, it will look like r is equal to a plus or minus b times, and then sine or cosine of theta. Where in this case, a is greater than b, but b is still positive, greater than 0. Then we have our limaçon with an inner loop. So now we still kind of look like we have a cardioid. That dimple is now still at the origin again, but we have this loop inside of our figure. And those equations are going to look like r is equal to a plus or minus b times cosine or sine of theta, where now b is greater than a and a is greater than 0. So we see just how making these slight changes are going to change the look of our graph quite a bit. On to our next value here. We have our lemniscate. Kind of looks like propellers there on 2 of your quadrants. In this case, your polar equations will look like r squared is equal to a squared times cosine of 2 theta, or r squared is equal to a squared times sine of 2 theta, where a is just not 0. Then next we have our rose with 3 petals. So you can also think of it as, it kind of looks like a propeller with 3 wings on it. So in this case, these equations are going to look like r is equal to a times sine or cosine of 3 theta, where a is still positive. Then lastly, we have our rose with 4 petals, which in this case, our equations are going to look like r is equal to a sine of 2 theta, or r is equal to a sine of a times cosine of 2 theta, where once again a is positive. So we see the slight changes. The cardioid, the limaçon without an inner loop, and the limaçon with an inner loop, these are all very similar. we just have some key differences going on, whether A or B are greater than each other, what they look like, switching out cosine and sine, things like that. Very small changes gives us very different results. For things like the lemniscate and the rows of 3 or 4 petals, these all look very similar as well, just with those slight changes. So we see how the graph of our equations change just by making those small changes there. So these are going to be very helpful when trying to work through equations, whether in our homework, quiz exam, anything like that. These are going to be really helpful. If you can quickly identify what kind of equation that your polar coordinate or your polar equation is going to be and you have to graph it, it's going to be very helpful. Instead of trying to go through and plotting each and every little point and then finally drawing it out, things like that. If you can identify what the actual shape is going to be, you can then narrow down to where your shape will actually have defined points, define just a few of those points, and then be able to determine whether or not it's reflected over your polar axis, your pole, or a certain line, pi/2. Which in that case would make it just that much easier. So, all right. Example 2, we have that we want to graph the equation r is equal to 1 plus 2 times cosine of theta. Now, we know our equation is 1 plus 2 times cosine of theta. Well, let's just take a really quick look at our other equations here. And if we take a second to really look at these values, we can see that our value of b is greater than a. So determining which one of our polar equations is going to be, we can determine that it's going to be the limousin with inner loop. So just by matching up this equation, we can already determine what kind of graph this is going to look like, and really how our equation is going to end up looking. But for purposes, we're going to go through each one of our steps and determining symmetry, and then going through and defining points. But we do know what it's going to look like in the end now. So once again, we have our polar coordinate system here. We have our equation given to us. First thing we want to do is check for symmetry. So in our check for symmetry, we're going to start with the polar axis. If it's symmetric about the polar axis, then this means that we should get the same equation whether or not we plug in a theta or negative theta. So our polar axis, we're replacing a theta with a negative theta. So in our equation of 1 plus 2 times cosine of now negative theta, cosine is an even function, so this will become 1 plus 2 times cosine of theta, which means that it is correct and it is going to be symmetric about the polar axis. So let's just make a note of that. So we get symmetric about polar axis. So remember, just really quick, this is our polar axis. Then now we want to check for the line pi/2. And for the line of pi/2, we're now going to be replacing theta with pi minus theta. So if we plug this into our equation, which is 1 plus 2 times cosine of theta, but now we're writing pi minus theta, we're actually going to end up rewriting this using our difference formula for trig functions. And when we do, this is going to end up giving us quite the equation. We're actually going to move this over because we need some room. This is going to become 1 plus 2 times cosine of pi times cosine of theta plus sine of pi times sine of theta. And when we simplify this down, we're going to get 1 plus 2 times cosine of pi is -1 times cosine of theta plus sine of pi, which is 0 times sine of theta. And this is going to simplify to 1 minus 2 times cosine of theta. So it does not give you the same equation as you started with, so we can't determine if it's symmetric about the line pi over 2. So it fails. We'll put the red X there. It fails, so it may or may not be symmetric about pi over 2. Then the last thing we're going to test for is the pole. Remember, if we want to do this, we're replacing r with negative r, or we're replacing theta with theta plus pi. If we replace r with negative r, this means that we're just going to get negative r is equal to 1 plus 2 cosine of theta, which we can just turn the negative into multiplying by negative of every other term, and this would end up giving us our value. Oh, my screen freaked out. Whoop, there we go. And did it again. All right, one more time here. So if we multiply each side by -1 to get our value of positive r, we would then end up with a -1 minus 2 cosine. I'm going to zoom out a little bit of theta. So that fails. Now we can also test for theta plus pi. So when we plug this in, we'll get 1 plus 2 times cosine of theta plus pi. And we end up just using the sum formula for trigonometric functions. So this ends up being 1 plus 2 times cosine of theta times cosine of pi minus sine of theta times sine of pi, which we simplify this. Cosine theta times -1 minus sine of theta times 0. And this once again gives us a 1 minus 2 times cosine of theta. So this fails as well, which tells us that it does fail, so it may or may not be symmetric about the pole, or in other words, the origin. All right, so we've determined symmetry. We don't know for sure about the line pi over 2 or the pole, but we do know for sure that it is symmetric about the polar axis. So now that we've checked for symmetry, now we can go ahead and test out some points. So a few things that we can do when we test points is we can determine the range of points that we actually want to test, because we don't want to test a million points, we just want to test a few very efficient select few. So we're going to continue on over here and say now we want to identify points on the graph by assigning values of theta and solving for r. So due to cosine's periodicity, and symmetry to polar axis, we are just going to test theta between 0 and pi. So we're going to pick important points between 0 and pi that we're actually going to test, and then whatever points that we end up getting, we will then just reflect over the polar axis. So we then plot these points and reflect about the polar axis. All right, so we have enough room here. We're going to draw out our table with values. So we're definitely starting with theta, and we're going to have r, which in this case we have r is equal to 1 plus 2 times cosine of theta. Let's go ahead and finish it here. And we're going to end up testing 7 values. Just barely. So we definitely want to start with the value of 0. We start with the value of 0, and we end with the value of pi. Now we want to fill in all the values in between. We don't have to test for every single significant value. We don't have to test for every value on the unit circle. We can just pick a few values to test. It'll be really helpful to test out any of those values that are going to give you a 1/2 or a -1/2 when you plug those values of theta into cosine. So you definitely want to remember to consider your integer multiples of pi over 3. Then when you have pi over 4 or 3 pi over 4, you're going to get a square root 2 over 2. And whenever you have multiple integer multiples of pi over 6, you'll end up with a square root 3 over 2. So between pi over 4 and pi over 6 are multiple integers of pi over 4 and pi over 6. It's really up to you on what you decide to do. But for this problem, I'm going to pick multiple integers of pi over 6. So we start with 0 and we end with pi. Then we're going to use pi over 6 and pi over 3. Cut it in half of pi over 2. Then we'll use 2 pi over 3 and 5 pi over 6. So we're going to plug these values into our equation. If we plug in 0 for theta, this is going to give us a 1 plus 2 times 1, which in this case is just going to be 3. So our point is at 0, 3. Then for pi over 6, we're going to get 1 plus 2 times the square root of 3 over 2. And we want to use a calculator to find this exact value. And when we do, it's going to come out to about 2.73, which means that our next ordered pair is pi over 6 and 2.73. Then for pi over 3, we get 1 plus 2 times 1/2, which is going to end up giving us 2. So our point here is pi over 3 and 2. Then for pi over 2, we get 1 plus 2 times 0, which is just 1. So our value, we get pi over 2, 1. For 2 pi over 3, we have 2 times -1/2. And this is going to end up giving us 0. So now we have 2 pi over 3, 0. Then for 5 pi over 6, we're going to get 1 plus 2 times negative square root 3 over 2. Using a calculator, we'll find this value. It's going to be about negative 0.73. So our ordered pair will be 5 pi over 6, negative 0.73. And lastly, our last value here of pi, this will give us 1 plus 2 times -1, which ends up giving us a value of -1. So this means that our point here is going to be at pi -1. All right, so we solved for 7 values here between the areas of 0 and pi. So we're going to plot all of these points and then reflect over our polar axis. Let's go ahead and erase this highlight here. There we go. All right, so our first point is going to be at 0, 3. So we find 0 on theta, and we count 1, 2, 3 concentric circles out to get our first point of 0, 3. Our second point is at pi over 6, 2.73. We're just going to have to estimate where that is between our circles. So let's say it's going to be about right here. Then our next value will be at pi over 3, 2. So pi over 3 and 2. Then we have pi over 2 and 1. Then we have 2 pi over 3, 0. So a point right here. Then we have a 5 pi over 6 is negative 0.73. So not quite a negative 1, probably right about there. And lastly, for pi, we have a negative 1. So if we connect these values, let's zoom in here so we can get a semi-accurate drawing here. If we connect these values in order of how we got them, we end up with a picture that looks like this. And remember, we're reflecting about our polar axis. And this is our polar axis. So we're going to reflect about this axis. Let's draw this in a different color so we know where we are going to end up being reflecting. We're still going to use blue so we know it is still going to be the same graph. But when we reflect, we're going to draw our points here. So that when we connect, our new points will have this mirrored image. We can draw some dots here to represent that this is still part of our picture, but we can make it separated, showing that we reflected this value. And look what we had. We had our limaçon with an inner loop. So our inner loop was a little bit different than what we saw in our given equation there. But that would be our final project, or our final, product there of our given equation. So all right, quite a few steps there. Once you've done a few of these problems and you can quickly identify what kind of problem it is, just for the sole purpose of quickly graphing things, you can definitely use a shortcut way of just identifying what your image is going to be, determining at what points you really want to find those key points that you're going to end up using to actually graph, and then deciding where to reflect over. So